morning. I'm Xianfeng from the University of Edinburgh. And I just noticed that from the program, actually my work is quite different from our yours. Actually, I is your backup. I just try to provide some radioisotope for you to do your research. So it's quite different. In here, I try to introduce some development by us. I think it's quite important for the study. So here I give one example for copper radioisotope, for the separation of the copper radioisotope from the nickel target. It's okay, can you hear me? Or from a nickel target, use the technique we developed called Cation-exchange chromatography to do this work. So before, this work actually it was done when I was at Birmingham University. Afterwards, I moved to Edinburgh University and teaching there. So firstly, I would like to say why we separated copper 61 and copper 64. So before, when I work on this, basically we produce some isotopes for two areas, one for medical physics and another for laboratory tracers for in application in engineering and science. So I working on the Birmingham Polytrain Imaging Center. So basically I in charge of the labeling and the isotopes productions. So in here I put the fluorine 18 here. Fluorine 18 actually is a very good radioisotope. It can be used in a very high purity. And also when we produce the fluorine 18, basically is produced from the water, pure water, distilled water. So there is no any other materials, other ions, chemicals interact for the labeling, and also it's very good for human body. But the problem for the fluorine 18 is fluorine 18 cannot label the chemicals. From here we can see I put a relative affinity of anions. So fluorine 18, if we put the tracer into the aqueous solution, the fluorine 18 can be replaced by any other anions except the hydroxide. So it cannot survive. And then we try to develop some other metallic radioisotope, for example, copper, gallium, and others try to do it. So in here I give a very brief, just 2 slides show other application. We also use the copper radioisotope try to label the trace particles for the study for the secondary pharmaceutical production. In here I give a tablet. In here, basically for each tablet, it only contain about 1%, sometimes 0.5% of active drug in the powder, in the tablet. So for all of you, I think you just use this. But for us, we do some research how to control the dose, have to be very uniform in each tablet. If the dose is not uniform, that will be disaster. So, but normally for pharmaceutical active drug, we have to mix with tablet and with the carrier materials. So there is a lot of things in here. So crystal shape, crystal morphology, crystal surface properties will affect. So we try to use a tracer to label it and study how control all these and see they can mix very well. So here just use some example. For example, we try to label active drug and then mix it and then use this one, you are familiar, and to check how the radioactive spread and then check whether the uniformly mixed. So that's some other application. And now I go back to the copper radioisotope purification. So the copper radioisotope we produce from the nickel target. So through all these nuclear reactions. So as we can produce copper radioisotope either from natural nickel or enriched nickel. Enriched nickel normally is very expensive. And so in this study, we try to produce it from natural nickel. And here is cyclotron, is M40 cyclotron. Try to use this to we use this to produce the radioisotopes. And this diagram on the right just show, so after irradiation of the natural nickel in the cyclotron, and then we can see from this spectra, we can see the copper 61 in here. That's a probe of copper 61. And then we need to separate. So when the nickel foil, after irradiation, when the nickel foil can produce some radioisotope. For example, if we use the 400 milligram of a natural nickel foil irradiated on 12 MeV deuterium for 90 minutes, we can produce about 7.4 millicurie radioisotope. So for medical physics, this is quite high dose. But from chemistry point of view, it's very, very small. So 400 milligrams nickel, after irradiation, we only produce 1.2 times 10 to minus 6 milligram nickel. So in the target, the ratio of nickel to copper is 3.4 times 10 to power 8. So this means in the target, the majority of material is nickel. Only very, very tiny is copper. So during the labeling, I think when you do a study, you already got the purified and separated radioisotopes. But actually, if we don't separate, it cannot use to label a tracer. If we directly use this label tracer from the reaction, you can see. So the nickel concentration is very high, so it will compete with copper. It's bind with the chemicals air. So the tracers, chemicals cannot be labeled, so we have to separate. So currently in the hospital, they normally use two techniques. Use a solvent extraction and also the anion exchange to separate the radioisotopes. So here I just give the copper radioisotope as example, and it's same for all others metallic radioisotope. And the third one is a technique we developed. So for example, if we use a solvent extraction, how it works? So firstly, when the nickel target, the nickel foil ready, we have to dissolve the nickel foil into 8 mole nitric acid. So in this high concentration, the metal foil will decompose into the salt. So we convert metal into an ionic state. And then we heat dry, dissolve this in the dilute hydrochloric acid. So make it into an ionic state and in low pH. And then we try to extract the copper, use the extraction. So basically what means extraction? So the copper has a high, strong affinity to stay with, go to some particular organic solvents. But nickel don't have the capability. Nickel will stay in the aqueous phase. And then we can separate the solvent phase and the aqueous phase to separate copper with the nickel. But in practice, the separation procedure is quite complex. It takes stages. So when we separate the extract, it doesn't mean all the copper will go to the solvent phase, all the nickel will stay in the aqueous phase. It's some portion. So for example, maybe 70% of the radioisotope go to a solvent, but 30% or 40% of nickel go to is also go to a solvent. So we need to strip and extraction again take quite a lot of procedure. So after the separation, the problem is a lot of radioactive material lost into the aqueous phase, and also consume a large of the chemicals, and the separation is still not very ideal. That's solvent extraction. And another one is called anion exchange technique. So here I put some anion exchange resin in here. The idea in here basically is when we dissolve the nickel foil into the high concentrated hydrochloric acid solution, so the copper will react with chloride ice, form a complex. This complex is selective charged. So basically turn to copper into a elective charged complex. So the elective charged complex and will be trapped by the resin, stay in the resin. If we go to a resin column, let the solution pass the resin column, it will stay into a resin. But nickel does not react with chloride, does not form a complex. So nickel still very positive charge. When we put the solution past the resin column, nickel will go out with aqueous phase. This is idea in theoretic like this, but in practical, it's not like this. So I put two data in here. So first one, we can see when we strip the column, use a concentrated hydrochloric acid, we can see the copper profile. The copper gradually come out. So when the acid solution add to until to 40 milligram is reached maximum. So after 90 milligram, all the copper come out. Copper radioisotope come out. It doesn't mean the copper just staying there. It's come out slowly. From here, we can see the nickel come out early. The right one, if we use a concentrate hydrochloric acid to strip this, the nickel come out quicker. So basically, we stop. For example, if we stop the hydrochloric acid stripping at, for example, 20 mil, and then we can get rid of most of the nickel, and copper will stay in the column. So here is a profile for the radioisotope separation. So we have two paths in here. Basically, for example, in here, this is the path. From this point, we change the solution. It's same from here, same from here. Before that point, we basically we use a high concentrated chloride acid to strip the nickel out. The blue square is a nickel come out. After nickel come out, and then we change it, use the water. Because when we add the water on, so from the reactions in here, the copper chloride complex will dissociate into copper ice. So when we add the water, it will turn to copper. So the copper will come out. So from the pink curve, you can see after add water, the radioisotope quickly come out, finish. So basically, we use this way to separate the radioisotope, copper radioisotope from the copper, from the nickel. But the problem in here is the separation is not ideal. So after separate, so from this we can see the copper gradually come out. After separation, about 32.5% of copper radioisotope will go to nickel portion, so it's lost. It will generate radioactive waste. And about 8 to 9 milligram nickel will go to a radioactive portion. So if we use this for human being, it's not good. But of course, I think that cancer patient is because they had very, and that kind of situation is no choice. Otherwise, if, for example, inject this go to the patient body, it will cause some problems. So we have to try to minimize the nickel portion in the radioactive portion. And before we develop this technique, so it have been in anywhere of the world is just use the previous two methods to separate. The reason is people said the typical opinion in here is, so they said it's impossible to use a cation-exchange resin to separate the metal with identical charge. So it is impossible. So nobody think about this. And from here, the relative affinity also show that. So all of the metallic ions, when they have a similar charge, their affinity to the resin is very close. It's very close. It's impossible. Why we develop this? Because we do some application. It's not only for medicine, and we also do some engineering application. We have to separate. If don't separate, we cannot do it. And then we think about some other way. We think, so the first tool has been used worldwide for many years. I think it's no point to put a lot of effort, go from there. So I think everybody is clever. They have done whatever have to. I don't think we are better than them. So we just give up, didn't touch the first two. Only this one I think is impossible. So we think maybe some way, because they just first impression, they think is impossible. So they didn't touch. Maybe some opportunity in here. So, and then we go to the reactions. From here we found, and the reactions basically, from all the reactions we found, one important thing here. One is ionic stress, and also another thing is the solution pH. So for all the reactions is controlled by the pH. So it means if we control the pH, may be able to find some solution. Another thing from here is another reaction, so the exchange coefficient. So for the exchange coefficient is not only determined by the thermodynamic complexation. This basically is purely depends on reaction and the resin. It also depends on ionic stress and solution pH. So from this we found solution pH maybe is a problem in here. And then we just do a pH test. So we do a pH test we found. So this is for separation of the copper and nickel. So at a different pH, use this is a resin column. The resin column is Cation-100. So afterwards, from this we found, yes, the common typical opinion is right. You know, when the pH greater than 2 is impossible. We cannot separate. They are overlapped. But only possibilities where the pH is very low, less than 2, only a very narrow range is possible. We can separate. So we found this, there is a possibility in here, and then we try to do this. But the pH is very narrow, so the separation is may not good. And then we look into the structure, chemical structure of the Cation-100, so see how the structure vary with the pH. So we found at low pH, the polymer is straight line, stay a straight line. At high pH, the polymer stays this shape. So these make very significant difference. At low pH, so the polymer is in line, so the resin is packed. The column is very, the resin is packed, pore size is very small. But at alkaline pH, so is that kind of shape. So it can be easy, the copper radioisotope can be easy hold between these. If like this, it's not easy. In here, copper can hold between these. So, but the separation have to be done in the low pH. But the good structure is a high pH. How to do this? So afterwards, we think we use something else. We use ammonium. We add some ammonium into the system. So ammonium is alkaline, can change the pH to strong alkaline. So the structure turns to this. And ammonium will react with this, stay in the column resin. So it can hold the structure. So when we add the copper solution, so at the low pH, the copper will directly just replace the ammonium, and then you know the resin structure is still like this, and it might be make it better. So, and then we do some test. So in here we try to use a two line. So for example, for a diagram at the left, so the bottom two curve is the solution didn't treat by the ammonium, but top two is treated by the ammonium. So we can see after treated by the ammonium, the copper, all the copper stay in the resin, does not come out. But before didn't treat, it's come out. And same in here, we use a different concentration of nitric acid. And afterwards we found, so there are two ways to do it. One is control the pH, another use ammonium to pre-treat the column, and then make the separation is better. So to do this, we also to check whether the ammonium affect the nickel's performance in the column. So we can see after treated by the ammonium, nickel's performance doesn't change. So that means the nickel does not stay in the resin, Cation-100. So it's just go out through the aqueous phase. And then we do some separation from here. So you see how the pH affect. So firstly, we pre-treat the Cation-100 column, use ammonium, and then we try to separate, add a solution into the column strip, use hybrid chloric acid, see how the concentration effect. So we can see from concentration 0.02 to 0.04, they perform very well. 0.02, 0.03, for these two concentrations, the copper can completely separate with the nickel. So, and then we do some tests, because the 0.03 hydrolytic acid is a good concentration. We do some separation. So these two diagrams to do separate just show the results for the separation of copper 61 from nickel. And the first, with the different doses, I think first one, the radioactivity dose is lower and another is higher. So from these two, we can see they can separate very well. And then here is some comparison. So the first, the chromatography, and if we use this one, the method is developed by us. So after separation, we can see if the initial radioactivity is 7.9, oh no, I think some unit is wrong, or 7.9 milli, I think here is micron, yeah. Yes, yeah, okay, micron. 7,800 micron curie. And after separate, so only 0.02 go to the nickel portion. Only 0.02 milligram of nickel go to the radioactive portion. And the radioactivity loss is only 26. But if we use the anion exchange resin, if we use, for example, just half of a dose, 3,700, and then the copper will copper radioisotope were lost significantly, about 1/3 lost. And also the nickel in the radioactive portion is reduced from about 8 to 9 milligram to 0.02 milligram. So we think this is a good method, and it can significantly improve the quality of the radioisotope. It's good for labeling, and also if for human body, it will be good for human being. Okay, that's my talk. Thank you very much. Copper 61, basically, we do some work, collaborate with Birmingham. When I was in there with some colleagues in the Queen Elizabeth Hospital. So they do some research, I don't know. So we provide to them, and they do their work. I don't know, they just use this. Yeah. They do research in the laboratory. Not, I think the two colleagues I collaborate, they do some research in the hospital, but I don't think they're directly working on a human being. Okay. Yeah.
Thank you very much. I have the pleasure to speak to you.
Okay, thank you.
Thank you very much. Thank you for your very nice presentation.
Yeah, thank you. Yeah, because I know when I come to here, I noticed when they invite me come to here give a talk, I don't know. When I arrived, I noticed my area is quite different from all of you. So basically, you are not really care about how to prepare this. You just take this to use it.
Also the first step. Your step is the first step. Okay.